8.5 acid-base titration. So, like I said, highlighter is handy. And to me, this is the meat and butter and bread and just the main chunk of Unit 8, which is why it's a long section. So I'll be recording this in different parts, so that way it's not overwhelming. Okay, so the first thing I'm going to do is recap from some unit ago, I can't remember, where we learned titration stuff. So this is pretty much review. So if there's anything that you need to review from this, review it, right? And so let's talk about stuff first. So titration curves for acid and bases. We have the pH on one axis and the volume of titrant in the other. And so it's showing how the whole titration works. And so we have something called the equivalence point, and it's when you have the titrant and the analyte being equal to each other in terms of the moles. And the titrant, we know the concentration of it, and that's what's in the burette setup. And then for the moles of the analyte, that's in the flask, that is the unknown concentration. If one is an acid, the other one is a base. So if the titrant is the acid, the analyte is the base, and vice versa, depending on the experiment. And so, since we don't know the concentration of the analyte, that is what we're doing titrations for. And it can be any kind of acid or base. It could be strong, it could be weak, just any of those situations, okay? And so the end point is when the titration is fully completed, so whatever that titration may be. And we use an indicator in order to see the change. And so the color change happens by protonation. And so protonation is whether a proton is attached or not. That's literally what it means. And so you can use Le Chat's principle to see, how the indicator is changing and stuff. So phenolphthalein is some indicator, so I'm just going to put IN. And so there's an H on IN. And then when it separates to its ions, then you have a pinkish color. So you have clear and pink. And we've used phenolphthalein before. Okay. So we choose an indicator where the pKa is equivalent to the pH or as close as we can, and it is at wherever that pH of equivalence is. So yeah, the pKa is at the equivalence pH. Your setup looks like this. So you have your burette here, you have your titrant and your analyte down here, and you have your flask, and then you're going to collect your sample. You know the concentration, and you'll know the volume you're adding because you can read it here. You know the volume you put in here, but you don't know the concentration. So make sure you remember this lab we've done before. Cool. So my honest recommendation for this section, besides having a calculator and stuff, is to look at the diagrams from 8.4. So we have a whole bunch of diagrams there, and so we can use that as a reference to talk about 8.5. And I'm going to, consistently try to reference them to the best of my abilities, so make sure you're looking at them too. So our first scenario is going to be strong acid and strong base. And so here is a question for that. And so we have a sample, hooray, hooray, hooray. And so it's measured as a function of the volume of titrant. And so we have our strong acid and our strong base, and we're making our reaction happen. So, cool. And so here's the generic where M is metal, strong acid, strong base, water, and then the salt, whatever the salt is. And so if I were to cross out all the spectators, then I would just be making water. Now, as a reminder, the H plus isn't technically hanging out in solution. It's usually hanging out as a hydronium, so that's why I can write it this way. I separated the two waters rather than writing 2H2O just to show the point of where this H is going on here to make water and water. So technically you could write that as 2H2O, but I just wanted to show that. Okay, so for when you're at a strong acid and strong base, your concentration of the H plus and the OH equal, and you're at pH 7. provided you are at room temperature. If you're not at room temperature, then it's going to be slightly different. Cool. So we have this titration curve here, right? And so we're going to analyze that real quick. A little bit of review, a little bit of new stuff. So again, we have our volume here that we're adding, and we have the pH here. And so make sure that you can draw a titration curve depending on who's adding what. And so I'm going to be talking about each point here on the graph. Now, before even doing anything, a question you can get on an FRQ is looking at this graph is like, what are you actually starting with? And so since our pH is low, it's less than 7, that means we're starting with an acid. So an example could be hydrochloric acid or something. So make sure that if you see where you, for example, the point starts, that you know where you're even starting at. So we know that in the flask there's an acid because literally it started at a low pH. So be mindful of that. Okay. So let's talk about each part. So A is like the initial part, give or take, right? Because it's literally right there. And so it depends on the concentration of that acid, whatever that acid is, right? And as a reminder, this little O here is the initial situation of anything. So in this case, it's the initial strong acid. And so because it's a strong acid, the amount of H plus is going to be equal to the concentration of the HA, which is also equal to the conjugate base. Obviously, if this was a different strong acid, you change the ratios a little bit. So like sulfuric acid, for example, is H2SO4, so just be mindful of that. And then part B, so part B is the pH before the equivalence point, right? Because it's any point here really, so we're just picking B, but it could be any point there. And so some of the acid, the strong acid, reacted because we are adding strong base currently, because this is C, volume of 0.10 molar of NaOH, so I'm adding base here. And so some of the hydroxides are reacting to the acid part, the H plus, or H3O plus to be more precise. And so here it is, so our strong base and our acid making water. And so pH is whatever H plus you have left over. And so if you remember from your pictures of your stuff on the example sheets, you want to make sure that you are looking at the scenario for that. So if you looked at, for example, the ones from here, our initial is this, where we only have the strong acid, and we're starting to add OH, so these situations is when we're start adding it. You can see here that one of the H pluses interacted with the water, and then we are interacting in that way. So, cool. Put that away. And so the biggest thing that's tricky that students mess up on is the new volume, because the new volume is adding from the sodium hydroxide and the acid on the bottom. So remember, the volume is new because you are literally adding solution into more solution. So don't mess that up. Very, very common mistake. Okay, so pH is at the equivalence point, and so again, that's when the moles of H plus and OH minus are equal, aka the concentrations of them will also be equal because they're in the same container. So the volume is going to be the same for both of them. And so we are at equivalence point. Now, again, as I said in the previous slide, if this is room temp, that means our pH is 7 for a strong acid, strong base titration. And then for the point D on the graph, so this is the pH after equivalence point, so we are adding more sodium hydroxide, and so pretty much the hydroxide, the OH minus, is overpowering. So it's going to affect the pH, and it's going to affect the pH more than the conjugate base. So as a reminder, you have conjugate base in the solution, technically, a little bit, and it's still not as strong as a strong base. So the strong base is going to overpower what the pH is in the system, and so that's why you're drastically increasing here based off that. And so be very, very, very careful about that. So to get pH, you have to get the OH, the concentration of OH, and the new volume. Be careful about the OH added past equilibrium because some of the moles had to neutralize, right? And so it's whatever extra OH minus that you have there. And then you'll have a new volume. So you get the POH, and then you use the formula pH plus POH is 14, and then reorganize it to get your pH. Good old algebra. Okay, so this is, again, another way of drawing the pictures that we saw before in section 8.4, but this is just to make sure that you're solidifying what you learned in 8.4 with the graph. And so here you have A, B, C, D, and here you have 1, 2, 3, 4. So you're going to decide which points are on which number. And so read this little tidbit on your paper / here, and then we have a little key here, and then I'll move this a little bit. And so pause the video and try to identify which drawing is which point on the graph. Alrighty, ready? Here we go. Ta-da! Oh, let me move this. Ta-da! So, I have my explanations on here. I don't have much to say other than the explanations are on there already, so I don't really have anything to add. So, if you have questions on this, make sure to ask me. Cool. All right. So, we're going to do calculations with strong acid, strong base. We've done a little bit when we were introduced to titrations, like calculating the equivalence point, but otherwise we haven't done like every single random part on a graph for this. And so I'm going to show you a new table rather than just the rice table because it's going to be handy. So, cool. Okay, let's move this here. Okay. Now, before doing anything, honestly, calculating the equivalence point would be very handy. And since this reaction is 1-to-1, excuse me, HCl and NaOH, if I wrote the reaction, we had it earlier, it is 1-to-1, and so I can use the MAVA equals MBVB with molarity and volume, and so the moles of acid will equal moles of base because it's the equivalence point for this, and so that's actually handy to calculate ahead of time. So, yeah. Okay, so concentration of HCl, we can get the concentration of HCl literally from just doing the equivalence point thing, because if I already know how much this is and like I know that they have to be equal, I could just math that and get it already. So you could do that. You can also read the graph and like reverse it from pH. That's if you can accurately read the graph, because obviously the axes, it might be small. So just be mindful of that. Cool. Okay. So the pH of the initial acid, obviously I already got the concentration of HCl, so the pH is 1. I could have also read that on the graph, but again, if the axis is not really readily available, then be mindful of that, so just be careful. Also, I forgot to mention, I got these 25 milliliters from the graph here, because here 25, boom, is the equivalence point, so I can find the concentration based off that equivalence point. Okay, cool. All right. What's the pH after 12.5 mils is added? So if we start at the initial, I'm adding 12.5 mils of the base. And so on this graph, I can see I'm like here-ish. Maybe I'm at B, maybe I'm a little less, I don't know. And so we can calculate the pH of that situation. Now, if I didn't have this graph, you should still be able to calculate stuff. Maybe not this part, but you could calculate other stuff depending on what is given to you. So remember, we have a new volume. That is the biggest mistake that students make, is the new volume idea, okay? So be careful about that. And so for the hydroxide, I am using the molarity that was given earlier, the 0.1, because it's right here. It's also right here. And then I have the volume I added, because it's 12.5 mils of the base. So I converted that. I cancel out my liters, and I have my moles. And then my H plus, I do the same thing. I had 25 mils because it is up here, sample of HCl. And then I had 0.1 molar because I calculated it here. My liters cancel out. I got my moles. And so I have my 2 moles, my H plus moles and my OH minus moles. And so my new volume is based off who's being added to what. So again, we started here and we're like at this point. So I have the 25 mils from the HCl. Remember, that's aqueous. And then I have the NaOH, which is also aqueous. Add those together. I get those mils. And then I convert it to liters because it's handy for calculation purposes. Cool. All right. So again, very common mistake that the new volume total is not calculated. So be very careful, okay? And so I get the new concentrations of these. You don't actually have to convert it right away. I do it just so I don't have to think about just sticking to moles and then dividing after comparing answers. You'll see what I mean in a second. I personally do it this way, but other people might just do the moles and cancel out moles stuff. Yeah. Now, I'm going to introduce a new thing. It's a BCA table. Now, the BCA table or chart, I might use chart sometimes, you don't need it, but it's a nice way to organize your thoughts. So I'm essentially seeing how much H plus versus OH minus is neutralizing from each other. And the BCA table helps. So BCA being before, change, and after, like I said here. So again, it's similar to rice, but it's just before, change, and after. And we're not at equilibrium in this situation, so that's why it's a BCA and not a rice, because rice is about equilibrium. The E is for equilibrium. And so I'm going to go ahead and fill out this chart based off the information we have. So before, we have these concentration of stuff, right? Because we literally just calculated it here. And so the change is who's neutralizing who. Now this is all 1-to-1 because H plus and OH minus. So that means I'm going to use up all of my sodium hydroxide to neutralize with that H plus. So my change is that these are subtracting because again it's 1-to-1. And so my after, so this is going to be 0, and now I have 0.033 molar of H plus left from the strong acid. And so now that I have this, I can check what was my question asking for. So my question was asking for pH. And so since I know how much concentration of H plus I have, I could literally just take the pH equation and then plug in my value to get the pH at point B, or maybe it was before point B. Again, I'm not quite sure where exactly point B is. But there we go. Cool. So again, BCA table helps. It's honestly just a stoic problem, but some students get confused about the stoic part for this, so I just have a BCA table. Again, you could just compare these and then use mole ratio to see how much you're using. So essentially, it's like a pseudo-limiting reactant problem. Yeah. Cool. Again, similar to a rice table, water is liquid, so that's why I didn't fill this out. So there we go. Cool. All right. D. What is the pH after 25 mils? All right. So the math is going to be exactly the same as this one, except, a different volume. That's all. And a different amount of base was added. So we're assuming it was from 0 and you added 25. So we're not taking this situation and adding an additional 25. We're assuming from initial to 25, okay? So be mindful of that. So again, same math as C. So I calculate my moles of each of the ions that we have from the strong acid and the strong base. I have my new volume. So both of them had 25 because again HCl started at 25 and then this problem has 25 mils of the base, and so I changed that to liters, and then I get the concentration of both of these, and then I'm going to fill out my BCA table. So the befores are, the ones we calculated already, and so if you notice it's 1 to 1, and so that means I'm going to use exactly the amount that they both are, and then my after is 0. So pretty much it fully neutralized, and so because I fully neutralize, all of it's water, and so my pH is now at 7. So again, if I go back to the notes that we took, this is the scenario 1 equimolar part. So if I go back to the Google Doc real quick, we were here, and then we're adding more hydroxides. And so eventually all of the acids reacted with the hydroxide and they all neutralized to the just be water. So just be mindful of which situation where we're at, okay? So that is pretty much here is where we are on the titration curve, okay? So be very, very mindful of that. Cool. Okay. And so what's a pH after 35 mils? Again, we're assuming we started at 0 and now we're at 35. So we are definitely at point D of the graph. And so here's the thing. You need to be very careful about the base. We used 25 mils at equivalence. So just to go back to the picture, 25 mils was used to reach this point. And so we added more OH. And so we're trying to figure out how much OH do I have left. And so the reason why I'm subtracting is because 25 mils again were used to neutralize all of the acid. There is now no more acid in that flask. And so now I have the base. And so I subtract them to see how much of the base I have left. And so I have 0.01 liters that are in addition to the water. So again, to go back to this picture, we are at this situation. I have over here my bases. And so those are the extra bases that are added. So I'm past equivalence point. And so I use the molarity of the strong base. So here it is. I cancel out my liters. I got my moles. And so my new volume, we had started with 25 mils of the acid. We added 35 mils of the base. So now I have 60 mils as my volume. And so I can get my concentration by taking the moles concentration of the hydroxide. I got my new volume here, and then I have my molarity here. Now the question is asking for pH, so I can indirectly get that by getting the POH. And so POH is negative log of the concentration of OH minus, and so I got that. And then we have the equation from our constant equation sheet. I'm going to plug that in here, and then I get my pH. Yay! Math. So the biggest thing that students get stuck on is this part here, is knowing, hey, we're past the equivalence point. So if you didn't have a multiple part question where you're going through every single thing, because this was literally E parts, right? So 5 parts. And calculating the equivalence point helps. If you can, obviously, depending on the information given to you, because if you know that you're past equivalence point, then you know for sure you're in the basic area. Well, for this particular situation, again, it depends on what's titrating what. But calculating the equivalence point first, very, very handy to help you visualize where you are in this titration. Cool. All right. So, here is the opposite situation where it's a strong base, strong acid. So we can see here we're starting off with a base and we are adding acid because we're getting more and more acidic. We're getting a lower pH. And so here's our problem. You can check it real quick. Oh, my question cut off. No, it's just the pH. So there we go. And so Again, notice it's the opposite direction. So we started off with an analyte that's the strong base. We have the strong acid being the titrant, so just be mindful of that. And so here's a quick mini return. So just like the previous one, you're going to look at these pictures and then identify on this titration curve which point goes to which picture. And again, water isn't shown. So try it out. Okay, ready? I don't have a slide for the answer, so I have to tell you. So number 1 is point D. Number 2 is point A. Number 3 is point C. It's all neutralized. And number 4 is point B, where you have half based and half neutralized. Cool. Now, I'm not going to go over a long example like the first example where we had the strong acid and the strong base be different compared to this one. They were flipped. But I'll just go over like another quick one just to make sure you got it, right? So calculate the pH with 12.5 mils of acid, right? And so similar math to before. I am not going to show all my math. But again, similar math where I calculate the moles of the H plus, the moles of the OH minus, the new volume, then the new concentrations of, or the before concentrations of those guys, and then these are the before concentrations. Then we see what neutralizes, so we're going to use up all the H plus. We have some OH minus left over, and so I can use the OH minus concentration to calculate the POH. And so POH is negative log of OH minus. And so then I can calculate pH with that one equation from our constant equation sheet. pH plus POH is 14. And so then I plug in my POH to get my pH. Yay. Cool. I also realized I wasn't checking my sig figs on any of these. Oh well. Whatever. Okay. So, here's a quickie your turn. I think it's quick, is it? Maybe. Sure. So try this your turn first, and then pause this, and then we'll see how we do. Okay, here we go. Here's number 1. Cool. Here's number 2. Cool. Oh, one thing I want to point out about this is I didn't do a BCA table. I wanted to show the other way of calculating because I said it's a stoic problem, right? So if you don't want to do a BCA, here's the way to do it the stoic way. I did do some shortcuts because you can see here it's 1-to-1, so I like skip some steps a little bit, but essentially it's just a stoic problem. So be careful, because you can see it literally here. We have the 0.005 versus 0.0048, so all of the OH is being used, and then we have a little bit of acid left over, which is why I subtracted it, because again, this is just limiting reactant problem. And then I have my new volume and stuff, so there we go. Cool. I'm going to stop here because this is part 1 of 8.5. We're going to talk about the other 2 scenarios that was from 8.4 and the calculations behind it. Okay, bye!